Hi everyone, my name is Mahmoud and in this video I will present our work entitled Rules Efficient Search for Customized Activation Functions with Gradient Descent. This is in collaboration with Lukas, Strack, and Frank. So activation functions are an important part of deep neural networks which affect their training dynamics and final performance. However, manually designing an activation function that suits a set of tasks has proven to be highly non-trivial. There's been attempts in the past to automate the process of learning activation functions. However, such approaches have all been based on black box optimization methods, which typically require thousands of function evaluations, rendering them highly inefficient. So the idea of this work is to apply gradient-based one-shot search methods developed primarily for neural architecture search to search for high-performing activation functions efficiently. For this purpose, we define the activation search as a computational graph shown here on the right-hand side, where we assign weighted sums of a set of unary or binary operations to each edge or vertex, respectively. And the set of unary and binary operations are shown here in this table on the left. In particular, we closely follow Dirichlet where a Dirichlet distribution of the operation weights is assigned to each edge or vertex, which is then learned in a bilevel fashion together with the network weights. However, due to inherent differences between architecture spaces and the space of activations, naively applying gradient-based NAS methods to the space of activation functions simply fails. We therefore have to make a number of non-trivial adjustments to adapt gradient-based methods to the space of activations. These include constraining unbounded operations by clamping them at a certain threshold, warm starting the search with the default activation, and importantly, progressively shrinking the search cell by dropping operations with lowest coefficients during the search. We choose the number of operations dropped per epoch to be larger initially and to decrease logarithmically. And finally, unlike Dirichlet for neural architecture search, where the sampled architecture is the same for all search cells within the supernet, here we reduce variance by drawing independent samples for different activations in the network. All right, so let's now move on to the experiments. We have performed the activation function search for the ResNet 20 architecture on CFR10, and the search is repeated with 5 different Cs, which listed 5 distinct activations. As seen here in this table with test performances, one of the activations outperforms all baselines, and all activations outperform the default available activation. The results also generate reasonably well to the CFR100 dataset and the SVHN dataset, as well as the larger variant ResNet 32. This table shows the search overheads, that is the ratio of the search time to evaluation time of the default value activation, and the overhead is always equivalent to less than 5 function evaluations, demonstrating the efficiency of our method. We repeat the experiment for the VIT architecture, searching on VIT Tiny on CFR10. You can see here that 4 out of 5 activations outperform all baselines, and this pattern extends to other data sets and the larger variant VIT small. These extremely small overheads in this case, which are all less than 1, are partly due to the reduced number of epochs during the search and the aggressive shrinking of the activation cell in the early stages of the search. Finally, we search on a small variant of the GPT architecture with 11 million parameters in the tiny storage dataset. And with an overhead of less than 1, we can identify 3 activations that outperform the default value activation in this model. And this extends to larger variants with 30 million and 65 million parameters, respectively. So to conclude, we have introduced a gradient-based technique that is able to identify top-performing activation functions and in a time equivalent to only a few function evaluations. As the first such work, our proposed approach is not intended to present the optimal search pipeline, and instead, we expect this work to open up a host of follow-ups with improved search settings and search spaces. Thanks for watching.